In this video, we'll talk about how to perform hypothesis tests and create confidence intervals for quantitative data. You'll see that there are many similarities to the procedures that we've used previously for categorical data. We'll talk about how to distinguish between the distribution for a sample mean and the distribution for individual observations, how to explain the impact of sample size on variability of sampling distributions, test statistics, p-values, and evidence against the null hypothesis, how to determine whether it's appropriate to use a symmetric t-distribution to approximate the sample distribution for a mean, perform hypothesis tests and obtain confidence intervals for means using R, and interpret the results of hypothesis tests and confidence intervals involving quantitative data. We'll refer to a 2004 study that looked at mercury accumulation in largemouth bass taken from a sample of 53 Florida lakes. If the mercury accumulation gets to be too high, exceeding 0.5 parts per million, then there might be environmental concerns. In fact, in Canada, the legal safety limit is 0.5 parts per million, although the United States has a restriction of 1 part per million. We look at a random sample of 53 lakes in Florida. This slide shows the first 6 lakes in the sample, so you can see that Alligator Lake has a high mercury concentration level of 1.23 parts per million in the fish from Alligator Lake. Lake Annie also has an even higher mercury concentration of 1.33 parts per million, while Lake Apopka has a low mercury concentration of 0.04 parts per million. The histogram shows the distribution of mercury concentrations in largemouth bass from fish from the 53 lakes in the sample. We see that in the sample of 53 lakes, the average mercury concentration is 0.527 parts per million with a standard deviation of 0.34 parts per million. We want to know whether these data provide evidence that the mean mercury concentration for all Florida lakes is higher than 0.5. We know that it is for our sample of 53 lakes, but maybe it just came out a little bit higher by random chance. The question we need to investigate is how unusual would it have been to get a sample of 53 lakes with a mean mercury concentration of 0.027 higher than the overall average for all lakes. In order to investigate that, we need to know something about the distribution of the sample mean for samples of 53 lakes. We'll use an applet from the website artofstat.com to investigate. At the top of the screen, you see a histogram like the one that we saw in the slides. This contains the individual mercury concentrations for the 53 lakes in our sample. Again, this first histogram shows the distribution for the 53 individual lakes. What I want to know about is what if we took a sample of 53 lakes from all the lakes in Florida and calculated the average mercury concentration? I want to know where that average would lie, or specifically how much variability exists in the distribution of averages. To do that, I'll take a sample of 53 lakes from our sample here. Now you may be saying, well, if there are 53 lakes to begin with and we sample 53, then we'll just be picking all the same lakes. And that's a valid point. So to mimic a situation where we're thinking about all the lakes in Florida, we'll take a sample and then replace the lake that we draw and put it back in. So we'll sample from the 53 lakes using replacement and end up with a sample of 53 lakes in which some lakes will come up more than once and others not at all. We call this kind of sample a bootstrap sample. Bootstrap sampling has become increasingly popular in recent years. We'll use the applet to generate a bootstrap sample. You can see the distribution of mercury concentrations in the lakes of the sample, and the average comes out to be 0.488. That average is plotted in the histogram at the bottom of the screen. Let's take another bootstrap sample, another sample with replacement. This time you see it looks a little bit different, and the sample mean came out higher at 0.538. That's plotted here. Let's go ahead and take 10,000 bootstrap samples and see what the distribution of the sample means looks like. You can see in our 10,002 bootstrap samples, the sample means typically come out pretty close to 0.5, maybe a little bit higher, but there's much less variability in the distribution of sample averages, sample means, than the distribution of individual lakes. This should make sense since sometimes a lake with a high concentration will come out, but then lakes with low concentrations will balance these out, and the average will end up pretty close to the overall population average. Let's go back to the slides. And I repeated this simulation of bootstrap samples in R using samples of size 10, 20, and 50. We see that the distribution of averages has a nice symmetric bell shape that we'll be able to take advantage of. And we also notice that the variability in this distribution of averages decreases as the sample size grows. There's less variability in the distribution of sample averages for samples of 20 lakes than for 10 lakes, and even less variability when we take samples of 50 lakes. The fact that these distributions are nice and symmetric will allow us to use a symmetric distribution to perform inference, just like we did for categorical data. Before we used a normal distribution or a Z distribution. When we're working with quantitative data, we'll use a T distribution. A T distribution is very similar to a normal distribution. In fact, if you look at the picture, you probably wouldn't be able to tell it apart from what we've seen before. In fact, there's a little bit more area out in the tails and less area in the center of a T distribution, but that distinction is unimportant here. For our purposes, it's reasonable to approximate the distribution of sample means with a T distribution as long as our data are roughly symmetric to begin with, or if our sample size is fairly large, say greater than or equal to 30. As long as our data are not heavily skewed. To see why it's important that our data not be heavily skewed, let's look at a distribution we've previously seen that was heavily skewed. This is the revenues for 2018 movies. We see the heavy right skewness in the data. And let's take samples of size 10 and look at the distribution of sample means. You see the distribution of the sample average here tends to be pretty right skewed, and the symmetric curve is a poor fit. Even when we go up to samples of size 30, the symmetric curve doesn't fit very well. By the time we get large samples, size 100 or more, the bell-shaped curve fits pretty well. So when we have heavy skewness in our data, we need very large sample sizes if we're going to use symmetric distributions. To summarize, in situations with right skewness, the variability continues to decrease as the sample size grows, and the sampling distribution becomes more bell-shaped as the sample size increases. In the next video, we'll talk about how to use what we saw here with the distribution of the sample mean and the T distributions to perform hypothesis tests and get confidence intervals for quantitative data.